Okay, so it's 1:45, and I welcome you to the session on applications, industry, computing, and medicine. We have 6 really interesting papers, and we'll get started right away with a paper presented by Yifan soon on visual exploratory analysis for designing large-scale network-on-chip architectures. And if you have questions, try to post them as soon as you have them, since we have a slight delay on YouTube. Having said that, I will share my screen and we'll have the first video from Yifan.
Hello everyone. Today I will be presenting a paper titled Visual Exploratory Analysis for Designing Large-Scale Network-on-Chip Architectures, a domain expert-led design study. This work focuses on the collaboration between computer architecture researchers and visualization researchers to design tools that address performance analysis challenges in the development of large-scale chips, especially network-on-chip systems. Let me briefly introduce myself. I'm Yifan. I'm assistant professor at William & Mary. Together with the co-first authors Huang and Shaoyu, we form a computer architecture research team. Our work focuses on designing new chips that deliver high-performance architectures. And we're currently developing wafer-scale computing devices that involve large mesh networks. During this process, we faced the difficulty understanding and parsing the simulation results, which led us to start designing a visualization tool. However, our visualization knowledge was limited, so we turned to our co-author Kate from University of Utah, who guided us through the visualization design process. Let's start with the problem we have at hand. In this project, we want to improve the architecture of wafer-scale computing devices. These devices are huge and deliver a tremendous amount of computing power. They have hundreds of cores on each side of the mesh.
I think for some reason the audio is not working.
Existing tools often lack the ability to effectively handle the scale of our network, which involves millions of nodes and links. This results in visual clutter and even performance issues. 2 is related to the nature of network-on-chip systems. While we check the network traffic, the problem of the network issue is rooted in the architecture. We need to understand the architecture cause of the network issue. For example, if the network is congested, why are all other cores communicating with just one core? If the network is underutilized, why are the cores not communicating? What are they waiting for? Since we could not find a tool combining network and architecture views, we developed our own tool. We name it VIS4Mesh. VIS4Mesh is an interactive visualization tool that supports spatial, temporal, and architectural analysis of network-on-chip systems. The tool helps computer architects visualize traffic patterns and link the patterns with architectural causes. VIS4Mesh integrates multiple views, including a temporal view for exploring network behavior over time, a spatial view for understanding network traffic patterns within the network, and the integration with Dyson visualization tool for more detailed architectural analysis. The temporal view shows network activity over time using stacked bar charts for traffic analysis. This view provides a clear representation of traffic changes throughout the execution period, helping to pinpoint when congestion occurs. Additionally, a heat strip is used to highlight peaks in the network usage, which is the highest amount of traffic on links. The heat strip makes it easier to identify congested links and the period of high activity. The spatial view uses a heat map to visualize traffic across links and nodes, which is instrumental in identifying hotspots and congestion within the network. The spatial view also includes a bird's-eye view, providing an overview of the entire network for quick navigation. This combination of detailed and high-level perspectives helps users effectively monitor and understand the traffic patterns throughout the network. Semantic zooming is a key feature of VIS4Mesh that allows users to adjust the levels of detail shown in both temporal and spatial views. We cannot show a million, of course, as it is nearly the number of pixels on a user screen. Therefore, we have to turn to a data aggregation approach. Starting from the finest view, when zooming out, the user will see an aggregated tile that includes a cluster of 4x4 tiles. As the user keeps zooming out, the 4x4 tiles disappear, and only the aggregated tiles are shown. This feature helps reduce visual clutter and makes it easier to transition between different levels of analysis. VIS for Mesh also includes an animation feature, which plays back temporal changes in network activity. This dynamic representation enables users to observe how traffic evolves over time. To assist the users in understanding the properties of the network traffic, VIS for Mesh includes a filtering capability. Users can filter traffic data based on specific criteria, such as the source or destination of the nodes, time intervals, distance of traveling, and types of communication. By toggling some properties in the filtering panel, users can tell how much traffic has a certain property. Finally, to allow users to identify architecture causes of network traffic patterns, we integrate Dyson, a computer architecture visualization tool. So when the user selects a tile and click the Dyson button, the Dyson panel opens, showing the task completed by the tile. This integration enables users to drill down into specific components and examine behaviors like memory access and packet exchange. By combining the temporal and spatial view of VIS for Mesh with Dyson's detailed architecture insights, users are equipped with a powerful toolkit for diagnosing and optimizing network-on-chip designs. So here, we want to summarize our design process. The design process was iterative and led by the domain expert. The architecture expert initiates the project and led the weekly meetings, while the visualization expert served in a consultative role. We find that the advantage of letting the domain expert lead the project is that the domain expert has control of the full data collection, data processing, and the result analysis workflow. The full control causes less friction in the design process. Whenever they find a problem, they immediately modify the data collection code and rerun the experiment to collect the data, which may not be easy if the visualization is implemented by a dedicated visualization team. However, this process is not without problems. In the design process of VIS for Mesh, domain expert initially preferred an intuitive approach without explicit task definitions, which led to the visualization experts to intervene. The visualization expert emphasized a broader task identification, and this intervention led to the conduction of a literature survey that focused on the mesh networks and performs metrics of networks. Through regular meetings, the visualization experts also refined the team's task understanding, resulting in a key design improvement like adding the heat strip in the temporal view. Though the task elicitation was new to the computer architecture team and met some resistance, their trust in the visualization expert made them open to the interventions, which ultimately ensure a more thorough and effective design. These interventions were both impactful and integrated smoothly in the team's workflow, enhancing the robustness of the visualization tool. In summary, we recommend for domain expert-led design. First, the domain and the visualization expert should establish a schedule that allows the domain expert to lead comfortably, with opportunities for timely interventions by the visualization expert. Second, domain experts need additional support for unfamiliar methods like task analysis and generating design artifacts. Third, early and regular discussion about research contributions and maintenance plan are important to reduce the friction of the project. Finally, teams should leverage the flexibility to extend the data collection, which is often enabled by the domain expert-led projects. In conclusion, VIS for Mesh is a highly useful tool for computer architects to analyze the performance of large on-chip networks. The project also successfully demonstrates the value of domain expert-led design, particularly in enabling tight integration between data analysis and visualization. By allowing architecture experts to lead, the visualization becomes closely aligned to their workflow, This study also highlights the visualization expert still plays a crucial role in guiding the methodology, ensuring the visual representation effectively communicates the data and facilitates decision-making. And that concludes my presentation. I appreciate your time to listen to my talk.
Okay, thank you very much for this interesting talk. I don't see a question on Slido yet, so I will start off with one question. So I found your paper very interesting. It combines a design study for network on chip architectures, but also quite some interesting thoughts on the design study, which is led by an expert. Does that also mean, I mean, it seems to me that it's necessary that you have a very close connection to this expert as the visualization expert and the domain expert. Is that an common scenario that you have very, very close communication? Usually these guys are always short on time.
So the question is how close we are with the visualization expert. So I consider myself as the computer architecture researcher. Like I design computer architecture, I design simulations, and our connection. So the whole project starts with a cold email with Kate, and then we start to communicate. I know her paper well before I start this project. Then I know he's working on some computing and some visualization, so I think that's a good match. So we start to connect. Then our connection and collaboration pretty much limits to weekly Zoom meeting. So then we received a lot of feedback from the visualization team. Of course, we can work on implementation of the visualization. We know how to write D3.js code. So we implemented the visualization, but we received a lot of feedback about workflow and skills and knowledges about visualization. That's how we collaborate.
There's one quick question here also from Slido. Could you share a bit about the process of training users to use this new tool, especially given their reluctance to share user requirements up front?
Okay, so basically our users are a very specific target, right? So there are computer architects and like PhD students in the computer architecture domain who design computer chips. So most of the training happens in project meetings and collaborative project meetings with other groups. Then typically we see this problem that they are reluctant to use these type of tools because they are more familiar with using terminal and printing data. Then we know there's a need, so we need to demonstrate this, help them solve a real problem. Then they start to like these type of tools. And then once they get used to these type of tools, they cannot come back.
Okay. Okay, so I guess people can catch you also on Discord to ask further questions. Thank you very much again. And we switch over to Shaolun Ruan, I hope I say that right, on QuantumEyes towards better interpretability of quantum circuits. Please take it away.
So everybody can see my screen, right?
Yes.
Okay, so let's get started. Hi everyone, my name is Ruan from Singapore Management University. And today I'm going to share our recent work, which is called QuantumEyes, towards better interpretability of quantum circuits. So here is a list of my amazing co-authors. And this paper was accepted by IEEE TVCG last year. Okay, so let's get started. So first, as you may already know, the quantum computing has already worked out from some textbooks and become more and more, practical and realistic. And the thing is like, no matter what kind of quantum application you're going to use, like quantum finance, quantum chemistry, or some even some quantum neural network, everything is based on the so-called quantum circuits shown here. Here is quantum circuits, and this one is the most fundamental and basic components in quantum computing. So here is the how people gonna visualize the quantum circuit, which is called a quantum circuit diagram. So as you can see, it consists of some wires here, which indicates the quantum bits, which is the qubits for short. And also it consists some quantum gates, as shown here, the block with a symbol H here. It indicates the Harman gate. So this is what it looks like for quantum circuit diagram. This is the most widely used visualization method for the quantum computing users. But here is some challenging things for quantum computing users, which is to understand the hidden quantum state changes. Like by using this diagram, you cannot tell how the quantum states evolute and generated from the very beginning of the circuit to the very end of the circuit, right? And you cannot tell like what's the functionality of each quantum gates. So for example, the Harman gate shown here, you cannot tell why we are going to use this Harman gate here and how this Harman gate changed the quantum states. So here is the change things. So to explain these functions, which is shown here, to explain the functions or functionalities of any quantum gates, we need the states before and after. So by comparing the states before and after, we can tell, okay, what's the functionality of the gates. So to address this issue, we propose a dandelion chart design to visualize the quantum states, and also a visualization system called QuantumEyes to enable the exploration of any static quantum circuits. But there are some challenges exist, like the current visualization for quantum states can only support less than 2 qubits, which are shown here. These two existing visualization approach is for the visualization for single qubit and 2 qubit states. The left-hand side one is the one called the blogosphere, which is the most widely used visualization approach in quantum computing area today. And it uses like the location of the points on the blogosphere to represent the amplitude, the phase of any quantum states, but this is only for the single qubit. And here is the visual design, which is for the 2 qubit state visualization. And as you can see, it consists of some like semicircles and rectangles here. But these two visualization cannot support like more than 2 qubits. Okay, so here is another challenge is like the number of basis states is very huge. Let's say we got n qubits, and it's gonna be power n of 2, right? So if we got 10 qubits, which is a fairly small number of qubits for today's quantum computer, but if we got 10 qubits, it's gonna be like more than 1,000 basis states, right? So here is the formula for any quantum states, which is the sum of the multiple basis states, like states 0, 0, 0, 0. This can be a basis states. So the number will be very huge. So here is what our dandelion chart looks like. Basically it visualizes the quantum states, and I'll illustrate the principles here. So first, we got a arbitrary quantum states which consists of multiple basis states, as you already know. And let's say we use multiple dots to indicate the amplitude here. The amplitude means alpha or beta for each basis states. And then given that the amplitude it consists actually it is a complex number, and it consists of a real part and a imaginary part. So we use a complex coordinate to locate the A and B. So this is how we locate the amplitude here. And sorry. And we also use a very big circle with the radius of the distance from the dots here to the original points. So in this way, the area of this very big circle can be represented like this, right? The pi multiplies the sum of the square of A and B. And at the same time, based on the quantum mechanism, the probability of this basis state can be represented like this, the square or the sum of the square of A and B. So in this way, we can use, which means that we can use the area of this very big circle to represent the probability of the basis states. Okay, so this is our initial design of the dynamic chart, and you can see there is a very severe, very severe overlapping and very clutter in this initial design. So we just simply reduce the area or all of the circles area with same factors k. Let's say the k here. So by doing this, we reduce all of the areas of the circles, and finally we got a proper k to take each very big circles apart, and then the overlapping and the veil clutter can be reduced in this way. Okay, so this is the final design of the dynamic chart, and by doing this, by comparing the multiple qubit quantum states before and after, we can tell the functionality of any quantum gates. And then we embed this dynamic chart design into the visualization system called the QuantumEyes, which can, as I mentioned before, enable the quantum computing users to explore any static quantum circuit. So here I'm gonna share a demo to illustrate how it's gonna work.
We use an example to illustrate the usage of QuantumEyes. First, we use an example to illustrate the usage of We use an example to illustrate the usage of QuantumEyes. First, we select the application we attempt to explore via the algorithm selection in the control panel. And then, the overview of probability summary visualization is displayed to provide users with a high-level summarization of the quantum circuit's behavior from the perspective of temporal probabilities. We then brush the specific steps from the view on the top to conduct a more in-depth analysis. As shown here, a state evolution view was rendered after we brushed the overview. This view can provide me with a more fine-grained picture of the evolution process of each basis state. We can hover on the specific basis state to perform a trace-back analysis, which makes us aware of how the basis state was generated from the beginning of the quantum circuit. To further understand the quantum circuit from the perspective of the qubit state, we can click on the symbol of the specific quantum gate. A table-like design will show up to indicate how a quantum gate can affect the quantum state regarding the specific qubit. Furthermore, if we attempt to enhance the confidence about the measured probability of each basis state, we can click on the background of the specific quantum gate. A novel geometrical visual design named the dandelion chart can be updated on the right side. This design can visually reveal the hidden rationale of how the amplitudes determine the final measured probability, making the measured probability more transparent and interpretable.
Okay, so here's a video to illustrate how it's gonna work. So here's some takeaway. So first, we propose a novel visual design called dandelion chart to visualize and explain the quantum states with more than 2 qubits, and also a visualization tool called QuantumEyes to better support the interactive exploration of the static quantum circuits. All right, so I think that's all for today's presentation. And if you are interested in our prior work, yeah, you can just take a look at our series of research papers, which are shown here. which is about the noise awareness, the quantum states explanation, and quantum circuits interpretability, and also the explainable quantum neural network. Okay, so I think that's all for today's presentation. Thank you, guys.
Thank you. We're pretty much out of time, but thank you for your talk. Maybe one quick question. Do you plan to use this as educational material also, or is that really for experts only? Find it quite nice to learn a bit more about quantum mechanics.
Yeah, I think both is okay. I mean, our tool can be used as an educational tool. Actually, we already did this because one of our courses already used our design to illustrate the quantum states in his classes. And I think it is also very helpful for some experts to observe the quantum states, because our design is the first one to support multiple qubits quantum states visualization, and you can directly tell and explain the probability like this via the location of the dots. So it is very convenient and useful. Yeah.
Thank you. Thank you very much for your talk again. Can you please unshare your screen, and we'll switch over to Xuan Huang, I hope I said that right, on her talk on bimodal visualization of industrial X-ray and neutron computed tomography data. Please go ahead.
All right, can you see the screen?
It's still in presenter mode, but yes.
Can you see the slides?
Yeah, you have to start the sharing.
Yes.
Yeah. Thank you.
We're good now? All right. So my name is Xuan Huang, and I'm from University of Utah. I'm here to present the paper Bimodal Visualization of Industrial X-ray and Neutron Computed Tomography Data. This is a collaboration between University of Utah and the Lawrence Livermore National Lab. So advanced manufacturing technique creates increasingly complex objects, forming internal features that cannot be opened for inspection. For example, on the left, we see a battery scan to validate the placement of each piece inside that pack. And then on the right, we see a cylinder head casting scan for car manufacturing purpose. Therefore, volume analysis serves as a non-destructive way to examine the material composition. The field uses two computed tomography scans, X-ray and neutron, to examine the data. However, neutron is low resolution. As we can see here, it does not extinguish the outermost material, the orange and pink one. While X-ray is unstable, it extinguishes the material at the outermost ring, but it does not detect the innermost holes as indicated by this little white dots in the ground truth illustration. Therefore, we need to combine complementary information. But how? Manual solution is labor-intensive, as someone has to go into the volume and label each voxel, and data fusion technique, which combines multiple channels into one scalar field, risk information loss. Higher dimensional visualization systems tend to introduce additional data interpretation UI, which kind of adds the complexity to the user side. The bivariate histogram, however, has already been shown to be effective for this type of task, that is to identify distinct materials from both X-ray and neutron data. Here is an example 1D histogram of a real-world data. So the blue distribution shows the X-ray, and the green one shows the neutron. So it's much more clear on a 2D histogram, as we see here on the right with an illustration, that each cluster maps to a distinct material. Therefore, based on the idea, we designed a novel interactive bivariate visualization approach for the co-registered X-ray and neutron acquisition of industrial objects. We present a novel application of topological segmentation of the bivariate histogram for efficient identification of material composition. We provide a combined view of co-register volume integrating the advantages from both modalities, and we also allow an interactive widget to be used for straightforward editing of the topological segmentation result. Here is an overview of our entire pipeline. So the first step, the material identification, is done through bivariate histogram segmentation, and the resulting image is used as a color map in our real-time interactive visualization system. So just by looking at the histogram, it's very obvious that what we want are distinct clusters associated with peak value areas that correspond to each material. That's why we go to the Morse complex. It's also called the watershed, which identify exactly all those local peaks. However, the resulting topological structure, the Morse complexes, need to be simplified to yield meaningful result. Otherwise, it would be just too noisy. So we modified the standard persistence-based algorithm to a relevance-based simplification in our case, because we want to prioritize distinct peaks over further dividing larger values. The result looks pretty good for our use cases. So as see on the left image, in the same number of segments, the relevant-based volume provide a much more better segmentation as a closer resemblance to the ground truth. And then on the right, we see that as we increase the number of segments, our result matches the manually segmented result very closely. So we also compare our technique to other clustering techniques, and we present that our segmentation provides very clear material boundary while avoiding artifacts from each individual scan. And then we proceed to the visualization and the rendering process. The visualization system provides a combined view of the co-register volume and the interactive widget for editing on the user side after the automated segmentation. So we look at the first use cases where we demonstrate like the quality of the material identification. So here we use the JH2A data, which is a physics-based simulation data. And as we see here on the very bottom, our segmentation result matches very closely to the manually segmented volume. The second data we use is the battery data. It's acquisition data, so it's real-world objects, and we scan it for the volume. We can see that with our system, we successfully break down the material that are not obvious on the histogram, because in this case, the histogram itself, it's kind of messy with these skinny lines and scattered dots everywhere. And then we also reveal the feature that is not obvious in the traditional slicing views, such as this ring-like structure on top of the battery object. So for the next case study, we will show how the segmentation editing tool will help with flexible material exploration. So here we have the JH2B data. It's a high resolution variation of the JH2A data we just seen. And here we start with the volume that has the internal pink material that's missing that's missing the internal little holes. So once we identify that, we'll paint directly on the segmentation. So here we painted green. And as we can see here, after the modification, a new material is revealed. So here is the breakdown of what happens when we paint on the segmentation and what's reflected on the volume. In next case study, we will show how our system could be used for data validation. So here we're using the XR05B data. This is the acquisition data. And as indicated by the histogram itself, the scan is kind of messy with all this bleeding and noise in the histogram itself. And it's more clear once we see the segmented volumes that there are some unusual alignments happening here. Those are possible results from flaws in the data production or data registration processes. In the very last case study, we show how our system can be used for object investigation. So here, this data is an unknown metroid scan that the scientists would like to look at it without actually opening it. So what they're looking for is metal, which corresponds to the upper left pink material in the image B, and the rest are just different parts of the rock. For evaluation, we have 4 experts in the non-destructive evaluation team that participate in this experiment, and the feedbacks are as follows. The pros include that this is a very efficient material identification, especially compared to what they use, like the manual segmentation drawing on top of the histogram. They also appreciate that the concept itself is self-explanatory and it offers a familiar view with like the existing technology they're using. It also requires very minimum data manipulation such that they are confident the results are authentic. The cons include that the segmentation itself is not as accurate as a data-driven approach, and that with some background knowledge, some expert would expect to extract geometries for service-like structures. As a conclusion, as confirmed by both quantitative evaluation and expert feedback, we have successfully developed a bimodal visualization system that provides an efficient overview for both modalities, is easy to navigate, and is easily understood by expert scientists. And that concludes the presentation, and I'm happy to take any question. Thank you.
Thank you very much for your talk. There's no question on Slido yet, but I have one. I saw in your paper that you were commenting on bimodal medical data, that you can might also be able to use your approach for this. Can you comment on that?
Yes. So like the underlying idea is pretty similar, right? So in the idea case, the X-ray and neutron, like a pair value would identify a distinct material. So if that's the case for other data set, like either medical data or like industry data, anything, if the density value would identify a distinct material, then yes, this approach should work well for a variety of data types.
I see.
Okay.
Great. Maybe I have time for one more question. We are also in my institute working a lot with new 3D printing materials and new very complex objects that
Yes.
can be printed these days.
Right.
I guess that's an application case as well, right?
Right. Yeah. So the data can come from like manufacturing, like in the like cars, as we see like batteries and stuff, and like 3D printing, because like it's kind of above our ability to physically inspect it. So yes, this whole system would be set it up for like increasingly complex this components and objects.
Here's one more question. Nice work, says Anonymous. Can you comment on how sensitive the method is to noise?
Yes. So that's why we modified our segmentation result, because we want to stress it and see how kind of reclutant it is to noise. So based on what we have seen, in practice, what we recommend people to do is that you would increase the number of segments to above what's actually there. And what you can do is that if there are too much noise such that you cannot efficiently segment it, the materials with like smaller number of elements, you increase it to maybe twice or 3 times, and then you merge them, which is very easily done in our like visualization tool. That way you have much more controlling precision. So yes, so noise is a big factor in it, and I think it's more like a case by case kind of sensitivity on that issue. But yes, there are we observe it, and in general cases, the segmentation responds pretty well to that. In a very extreme case, there are ways to deal with it, but just more like kind of manual optimization and editing would be involved. Yes.
Okay. Thank you very much. You can continue the discussion maybe on Discord.
All right.
Thank you once more, and
you.
we'll move over to our fourth talk given by Rainer Splechtner on interactive design of experiments optimizing a cooling system.
Yeah, thanks, Xuan, for your introduction. And good evening from Vienna. I'm a researcher here at the VIS in Vienna, and I'll present our work regarding interactive design of experiments optimizing a cooling system. This work was conducted together with colleagues from Virginia Tech and the University of Bergen, and in close cooperation with the domain expert from AVL, who is also a co-author of this paper. The optimization of cooling systems is important in many cases, for example, for cabin and battery cooling in electric cars. On the right, you see an example of a simulation model of an air conditioning system for the cabin of a passenger car. The optimization of such systems is governed by multiple conflicting objectives, and it's performed across a multi-dimensional parameter space of control and output parameters. The simulation models are characterized by their nonlinear behavior and can only be linearized locally with a small range of sufficient validity. To the computational complexity of the necessary iterative numerical simulation, it's not feasible to densely sample the multidimensional parameter space, and inverting the simulation model is not possible. The extent of the parameter space, the complexity of the nonlinear model of the system, as well as the time needed per simulation run necessitate an iterative semi-automatic approach. So we present an interactive visual optimization approach where the user steers an interactive, iterative guided optimization process from within a visualization component we call interactive design of experiments that integrates simulation, visualization, and deep learning. The design of experiments methodology is commonly applied to simulations utilized in the automotive domain. It encompasses planning, conducting, and analyzing controlled simulation runs with the goal of gaining insight into a system's behavior with a minimal set of runs by applying statistical methods and varying multiple parameters simultaneously. So in short, we want to efficiently and effectively sample the large parameter space. Our approach has two phases. First, the setup phase, which is done offline, non-interactive, and only once. So we create an initial ensemble using the simulation model, providing a sparse yet as large as feasible sample of the parameter space, using a classical design of experiments approach as described before. Then we train a deep learning model to attempt an inversion of the simulation model using the initial ensemble so that we are able to suggest likely responsible control parameters for a certain desired system behavior. And then the second phase is the interactive iterative optimization phase. The visualization component serves as the central interface, enabling the user to interact with and to interpret the data. So of course, firstly, we can visualize and explore the initial ensemble. And then for each iteration step, the user can specify desired system behaviors, meaning output parameters, and then request estimated control parameters for the specified outputs using the deep learning model, which acts as an approximation of the inverse system model. Then the user requests new simulation runs for values at and near the estimated control parameters, and the ensemble is refined. The new simulation runs are also used to further improve the deep learning model. Employing the interactive visualization component, the user can then compare the computed and predicted outputs and sample the parameter space in the vicinity of the predicted parameters further to assess the quality of the prediction solution and compare computed and predicted outputs of the previous iterations. So summarizing, we use an initial ensemble, computed offline, and actively guide the refinement process by specifying desired outcomes in the interactive visualization. Using our deep learning inversion model, we estimate the corresponding control parameters for these outcomes. The numerical simulation then computes the actual outcomes for these estimated parameters. This guided iterative process enables us to progressively improve the sampling of the parameter space, focusing particularly on regions that likely produce desired outcomes, hence the term interactive design of experiments. Engineers represent the cooling cycle in the pressure enthalpy or pH diagram, a standard diagram in cooling system design. It shows the refrigerant's pressure at the y-axis and its specific enthalpy on the x-axis. It provides a visual representation of the refrigerant's thermodynamic state as it traverses through the system's components throughout the cooling cycle. The refrigeration cycle shows up in the counterclockwise direction in the pH diagram. The points 1 through 4, shown in red here in the diagram, are indicators of the efficiency of the cooling cycle and are called characteristic points. They are calculated by the numerical simulation, meaning they are output parameters. The connecting lines between the points correspond with the state changes in the cycle, as you can see written on the left. It's also important to note that the points are interdependent, mean that, for example, the points 1 and 4 have the same pressure, and 2 and 3 also have the same pressure. Typically, when designing a cooling system, the engineers do not specify these points directly when describing the desired cooling cycle characteristics. They specify low and high pressures and subcooling, superheating temperatures of the cycle instead, and the characteristic points can then be calculated from these values. We introduced the interactive pH diagram as our central visualization and interface, where we can specify desired system characteristics. Alongside the initially computed points, we have predicted parameters and computed cases based on these predictions, as well as several refinements at each iteration. To visualize these variations, we utilize point size and color, distinguishing between different cases and iterations. So in this case, the initial points are shown for context in gray and very small. The specified points are depicted in red, and the calculated points in blue, and the size depicts if it's the direct calculation from the predicted parameters or in the vicinity of these parameters. We have many options to configure this diagram, also with strong isolines and quadrilaterals. While the diagram conveys a wealth of information, it risks becoming cluttered when all elements are displayed simultaneously, of course, and there's a need to filter this efficiently depending on the task at hand. For example, when specifying the desired cycle characteristics, details of the initial points are not of interest, but the convex hull of the initial points is, since it gives a good indication if the current specified cooling cycle characteristics that are represented by the 4 characteristic points can be achieved within the system's plausible parameter range. The pH diagram explicitly depicts pressure and specific enthalpy, while temperature, quality, entropy for each characteristic point can be inferred from nonlinear isolines. However, interpreting values based on these nonlinear isolines is challenging. To simplify the analysis, we provide a dual representation of the pH diagram using 4 scatter plots. Each scatter plot shows additional aggregated values closely related to its characteristic point, reflecting its position in the cycle. To aid association with these points, the scatter plots mirror the arrangement of the points themselves. We experimented with 2 alignment strategies, grouping the scatter plots together on one side or distributing them across 2 opposite sides to align with the original points. The latter arrangement with the 2 plots on each side was clearly preferred by the domain experts. Besides the interactive pH diagram, we have integrated additional views into our coordinated multiple view setup, parallel coordinates in the box plots view, the parallel coordinates views for showing the simulation control parameters, and the box plot depicts statistics. They provide an informative overview of the development of basic descriptive statistical values across iterations. So, and now a short video. So the initial ensemble is shown in the coordinated multiple view setup here in gray as context. The user specifies the desired target values for the cooling cycle in the user interface, and the 4 characteristic points are shown in the pH diagram. Now the user presses the predict button, and the deep learning model predicts the corresponding control parameters. They are shown in the parallel coordinate view. The compute button is pressed, and the simulation calculates additional simulation runs with the predicted control parameters and parameters in the vicinity. We specify a new set of target values and initiate a new iteration. We also start a 3rd iteration. As before, the control parameters are predicted by the deep learning model, and the ensemble is refined, and the view is updated with each new simulation run. We configure here the box plots to show the energy flow in the system split by iteration, and we also show the reference point in green here to compare different iterations to the default value and evaluate that optimization goal is achieved. So, concluding, the interactive design of experiments approach enables a rapid guided optimization across a multi-dimensional parameter space based on an initial simulation ensemble that is stepwise improved using two models, one for the numerical simulation of the system, as well as one for its approximate inversion. Our visualization design of an interactive pH diagram enriched by a dual perspective on the data serves as the central interface for the guided interactive optimization, and a use case demonstrating the successful application of the approach can be found in the paper. Thanks for your attention.
Thank you very much for your talk. We are a bit short on time, and I don't see a question on Slido. So I ask you please to ask Rainer questions on Discord for his talk. And thank you, Rainer, once more for your presentation. And please unshare your presentations so that Gabriela can start. And she asked me that you all crank up your volumes during the presentation video at least. So please take it away, Gabriela. On data loss data, I will keep it short.
Okay, hello everyone. I'm Gabriela, and I'm of the University of Zurich's Interactive Visual Data Analytics Lab. Daedalus Data is our design study that we've done with our research colleagues at Roche over here, Alex and Amanda. And in it, we studied data exploration and knowledge externalization through the labeling of particle images derived from a medical manufacturing context. So to diagnose diseases early and correctly, in vitro diagnostics have to be accurate and reliable. And this requires that the specimen, the test equipment, the test materials are all free from harmful defects. So we partnered with Roche's product quality engineers to solve this quite critical problem, this particle contamination that's present within in vitro diagnostic consumables. What you see over here are how Roche engineers track their observations of contamination with photographs. So each one of the photographs here is one image of a contamination processed through some internal algorithm they have to identify, quantify, and measure it. We studied over 37,000 of these images coming from 70 different production lots and abstracted them in a way I'll describe in a minute. So the challenges that happen from this setup is that the particle amount exceeds visual pattern identification possibilities for users. The multivariate particle characteristics that they keep track of can only currently be investigated as a subset, not as a whole. And that means that expert knowledge is not systematically captured or used in sense making. So working with this abstraction of the image and production context, we prepared feature vectors of these attributes here, and these represent what manual expert evaluation would have considered. Daedalus data then augments the dataset with expert-developed labels organized into label alphabets on the left here, and this means that data abstraction is a continuous process that is extended throughout regular use of the tool. I'll come back exactly to how that happens after we talk about our requirements. These we've derived from stakeholder interviews early in the process, and we organize them around data exploration, ensuring that experts can effectively interact with and query the particle data to discover new patterns. Also labeling through multiple selection and inspection modalities. And these two together in turn lead to knowledge externalization in the creation of labels and their organization. So altogether, what we found was that there are two iterative nested workflows at play, one for exploration and labeling, and the other on the overarching knowledge externalization process. To answer your question of how all these workflows are realized, I bring to you our generalizable framework for enhancing data exploration with data augmentation. We support two control modes for experts to steer the particle display with. Each crosscut here is going to exhibit one type of control. On this vertical axis, we see the separation between attribute and projection-based views. These differ in that the attribute view shows a layout based on a single attribute, and the projection view for multiple user-specified attributes. On the horizontal axis, we'll see the influence of pre-existing attributes on these views versus the additional impact of augmentation done by expert knowledge. So here, these two views are made of only pre-existing attributes. The top is a bar chart-like layout of particles, and the lower is a semantically meaningful projection. Each particle there is placed with respect to its similarity to neighboring particles' image and production contexts. Here, we see the extension of the bar chart-like visualization to accommodate for the enrichment that's done with expert labels. And this updates as users iteratively build the knowledge base of relevant attributes as they explore. Now, my co-author Alex is going to show us how this actually works, and I recommend you turn your volume up.
Having received a complaint for lot 27, an expert can structure all particles by the lot number attribute and view the column of the specific lot. Being able to visualize all particles of one lot in this structure reveals a high ratio of blue particles.
Okay, now you can see how multi-attribute projection is improved by user enrichment, with projections recalculated as new labels are included. And additionally, you can see how the entire right side of this matrix is designed to support an expert knowledge elicitation process. Experts are a part of the data enrichment throughout our entire approach. Okay, let's bring Alex back to show us an example.
Aside from free exploration, the highlighted blue particles draw the expert towards the existing blue particles, to which similar ones are now positioned. This enables the expert to find similar particles of interest and directly add the blue label to them. Externalizing expert knowledge through labels allows experts to focus back on one attribute.
Lastly, we have 4 auxiliary views. They perform our labeling, facilitate interactive drill downs, particle selection, and detailed analysis. Let's bring back Alex one last time.
The view allows experts to apply attribute-based filtering, refining the dataset and observing the effects of the canvas. The selection view reveals summary statistics on particles currently selected by the expert on the canvas or through the label view. The detail view displays an enlarged image of a single expert-selected particle along with its image and production context attributes. The labeling view allows experts to define, highlight, select, and modify labels and alphabets, translating domain knowledge into actionable labels.
Okay, so our label-informed projections that I keep harping about work similarly to this classical example of semi-supervised UMAP on a benchmark dataset. Compare these two clusters in the unsupervised and supervised cases. In the semi-supervised case on Fashion MNIST, we see the best of both worlds. We see semantically meaningful clustering while we reduce the expense of obtaining new labels. We also benefit from this semi-supervised UMAP dimensionality reduction in our own projection of particle images in Daedalus data. The label alphabets become known semantics to the system, used as user-specified attributes, and lead to similarity-preserving positionings. Our projections are similar to those we see in systems like Pixplot, and this dynamic labels approach is similar to our own iterative labeling workflow. And I've also included a few other notable examples. What we focused on was incorporating this type of foundational work into moving beyond visual summaries, like refined representations based on both computational methods and human insight. Our case studies really reinforce this. What we heard is that the key is not replacing expert intuition, but augmenting it with data-driven insights, something I'm sure many of you have heard many times throughout this conference. Our task-based evaluation included a think aloud protocol where we observed the experts in their organic workflow with minimal disturbance as they tried to complete these tasks on the left. We outlined these tasks, but as you can see in the case of expert 2, in task 1, they first identified a group of particles and then were quite excited and really ran with their analysis. And so they did not complete it. But overall, even despite that, we got very positive responses. And we also observed in this last image at the bottom, very varying workflows with participants consistently and equally using both the main and the auxiliary views I mentioned to go about their tasks. While we reflected on lots of concepts, as you can see here, I'll leave you with just 2 direct questions. The first is, what's the correct balance between human work and automation? So while automation offers efficiency, of course, it cannot ever fully replace the depth of insights that are provided by human experts. And my second question is around quantifying success. How do we assess the longitudinal impact of such a learning approach? A system's effectiveness could be measured in time savings, in cost reductions, in improvements to environmental sustainability, but which are the right facets to take a look at here? To conclude, this project stemmed from a need of our collaborators to better understand the relationships within their dataset, and our tool allowed them efficient and iterative ways to do so through our label-informed projections. Our framework leveraged labeling to externalize engineers' expertise, and this allowed for deep exploration of their large and multivariate dataset for the very first time. Thank you so much for your attention. We have an online demo that is currently under construction at the first QR code, and our lab is also hiring postdocs and PhDs at the moment. So if this interested you, please scan the second QR at the bottom.
Thank you very much. Great talk. So you had some discussion points here while I wait for a question on Slido. So what do you think you found the right way of automation between human, or collaboration mode between human and machine in this case, or where do you think your work is going in this direction?
Right. So my work looks a lot at human AI collaboration in general, not just with image data sets. And I think what we have found is a really effective and efficient way to do so. But what I have been saying, like in the discussion as well, is that unless you do like this long-term longitudinal study that looks at how work changes as these tools are implemented and introduced into workflows, it's really hard to tell how effective you're being. Like we went from a situation where no such tool exists and people do things manually into the first introduction of such an automation. So yeah, work is going to change like in a collaborative way and in a time sensitive way. And it would be really interesting to study that long term in general. I think if anybody is doing any work like that, I would really love to hear about it, because I think that literature is really missing at the moment.
So is your tool already or your approach that you developed together with Roche, or in collaboration at least, is that already on its way to being part of a workflow, since we're here in this application session?
Yeah, they're quite careful with introduction of new tools, so they're kind of slowly ramping up to it. Yeah, but we did have real experts using it who are part of the same team that would be doing this manual assignments. So we got really positive feedback. We can only hope that it keeps being implemented and introduced to the team.
Thank you so much for your presentation and the question and answering. I'm sure that there will be more on Discord later on. And we come to our last talk given by Andrew Wenzel, called Ditto, and I leave the rest of the title up to you, and please go ahead.
Okay. Can you see? Okay. I am Andrew Wenzel, and I'm presenting Ditto, a visual digital twin for interventions and temporal treatment outcomes in head and neck cancer. I'm from the USC Electronic Visualization Lab, and this work was also in collaboration with the MD Anderson Cancer Center and the University of Iowa. So meet Alex. Alex is a head and neck oncologist at the MD Anderson Cancer Center. And when planning treatment for a new patient, Alex has to consider not only the existing guidelines, but also their memory of past similar cases that they've seen. And this is because while guidelines exist for the treatment of patients in many cases, these tools are generally very complicated and don't handle exceptions well. For example, the actual guidelines at their current institution ask Alex to consider alternative treatments 11 different times with no additional explanation. And while deciding on which therapies to use and which combinations of therapies to use, Alex needs to not only consider treatment effectiveness in terms of both survival and tumor control, but also the side effects of treatment, which can impact patients' quality of life long after treatment is completed, which is a kind of rising issue with the large survival rates that we're seeing. And because of the complexity of this decision-making process, there's an interest in using digital twins to support decision-making. Digital twins are a general concept for the virtual representation of a real-world object or process that can be used to simulate and predict behavior. While digital twins have been used in the past in engineering and other fields like engines or exascale data centers yesterday, In our case, we model a sequential human decision process. So in this context, we are making digital twins of the physicians who are interacting with simulations of the patients via treatment decision, which are the actions, and then we can use reinforcement learning to learn a policy for this physician. So in the clinic, determining the best course of treatment requires dynamically adjusting the treatment based on the patient response to each step in this treatment process. And most computational models for helping clinicians usually only look at the initial diagnostic factors. However, with digital twins, we can dynamically predict how a patient might respond to treatment in a sequence and identify overall treatment policies that can consider these patient responses at multiple stages in the process after the initial diagnosis. And the idea is if we combine this with visualization and explainable AI tools, we can use both the simulated policies and the simulated patient responses to help clinicians make better treatment decisions when working with patients. So the work that we're talking about was developed as part of a multi-year collaboration between oncology radiotherapists at the MD Anderson Cancer Center, machine learning experts, and visual computing researchers. Our group previously has a published reinforcement learning-based digital twin for simulating therapy outcomes and determining optimal treatment plans for oral pharyngeal cancer, which is referenced at the bottom of the slide. And this work, we made several extensions to this, as well as built a front-end interface to support clinicians working with this model. The specific contributions of this paper are requirements engineering of the human factors that oncologists consider when interacting with digital twin systems for treatment planning, the design of one of the first interfaces that leverages digital twins for clinical decision support for oncologists, with a focus on looking at both skepticism and appropriate trust in our models, and finally, a qualitative evaluation of the system and design insights. In terms of related work, there's been various projects that have investigated interfaces for decision support for clinicians and interfacing with digital twins. However, to our knowledge, there's not anything that has done both, and this is one of the first attempts at a digital twin for decision support that includes sequential decision policy modeling for oncologists. For our design, we used an activity-centered design approach. So we gathered requirements with interviews through 3 research oncologists in our group, and then we gradually refined through multiple rounds of parallel prototyping our design. After we settled on an initial design, we showed this to a group of 11 different oncologists from the MD Anderson Cancer Center and got feedback on that before finalizing our design. Through requirements engineering, we identified a few main challenges that I will briefly go over. First is sequential decision-making. Second, we have a mixture of several long-term and short-term outcomes that are both binary and longitudinal in nature that we have to communicate to clinicians without overwhelming them. Third, we have some complex model results that we need to communicate to physicians while ensuring that they are simple enough that the clinicians require minimal training to understand what they're seeing. And finally is what we're calling appropriate trust. And in this case, because our models are not perfect, but they're better than guessing or kind of nothing, it's important to give recommendations that allow for model introspection and allow physicians to identify cases when the model should or shouldn't be trusted. So as a way to think about appropriate trust and how to approach this, we can consider how a clinician normally reasons about their data. We know clinicians usually rely on multiple sources of input, such as guidelines from their institution, other doctors, and previous similar patients that they've seen. And they also have to balance like survival and side effects. So our digital twin already considers patient survival risk as well as previous physician decisions and looks at the balance between tumor control and side effects. However, to support skepticism and make people think more slowly about their data, we decided to also model an approximation of similar patients using a KNN and average treatment effect to look at the effects of different treatments. And we can show the recommendations from both of these models to the physician when we're showing our results. And in the cases when the model disagrees, this can prompt the clinician to like pause and slow down and look at the explanations as to why these models are making their decisions. Another advantage of this is that with the KNN, we can show the individual patients in our data set to help the clinician think about it that way, since a lot of physicians use that workflow. So I will give a brief demo of the system. On the left here, we can have the model inputs, which specify the decision we want to investigate, as well as which kind of model we're looking at. And then we input the patient features, which include demographics, clinical diagnostic data, as well as some spatial information, such as the tumor location. In the center, we have some long-term survival plots of the patient, which have both models, as well as the case if the patient is treated or untreated. And then we have another view with additional binary outputs for all of the things we're modeling. So in this case, the patient has no significant difference in the predicted survival rates if they're treated or not, which is why both of these views are overlapping a lot. In the top right corner, we show treatment recommendations along with indicator of the patient's similarity to the training cohort, which can help us flag outlier patients. In this case, the digital twin and the naive model are disagreeing in the recommendation. The digital twin recommends against concurrent chemotherapy, while the most similar patients did receive concurrent chemotherapy. So to investigate this, we can look at the view in the bottom, which shows different features and their attributions into the deep learning model recommendation. And if you go to the bottom, you can see that the digital twin's main reason it didn't recommend concurrent chemotherapy was because this patient had a very low pathological grade, which a clinician can compare to kind of their existing knowledge to verify if this makes sense or not. This view can also show the similar patients used in the nearest neighbor-based model, with averages for the patients that received and did not receive chemotherapy at the top. And below that, we show individual patients ordered by similarity. So if you kind of zoom in here, you could see that the group treated with concurrent chemotherapy had a higher diagnostic staging than the untreated group, as well as the current patient. So this patient is more similar to the patients that did receive concurrent chemotherapy for this reason. In the paper, for brevity, we evaluated data with 2 case studies with the domain experts and got qualitative feedback from the debriefing interview from our workshops. Additionally, we have a quantitative evaluation in the supplementary materials because that is way over the page limit. Finally, we have design insights from our design. The first is visual scaffolding, and this is just relying on plots and anatomical diagrams that are similar to clinical tools that clinicians already know. Our original designs had some novel encodings, like histograms and some custom glyphs, but these were not received well in our workshop because people were very confused about how to read them. 2 is account for different information-seeking needs. So we found, especially in the workshops, that there's a variety of things people were actually interested in for when they make decisions. And some people only wanted the survival plots, and some people were very interested in, for example, the similar patients. So you have to kind of assume that there's different levels of information people want to see. And 3 is using multiple approaches to balance users' expectations of the model. So in our designs, we relied on the showing model prediction side by side, flagging outliers, showing confidence intervals when possible, and placing the feature attribution plots prominently in our views. Regarding the model of the system, our model currently looks at 3 major decision points that were given as critical points by our clinical collaborators. In future work, we can extend this when we get more data, because usually treatment is a very dynamic process. In terms of generalizability, we are looking at oncologic head and neck cancer patients, but this basic design can be extended if you have the data to other kinds of cancer. And finally, it should be noted that our models can inherit some bias because we're looking at clinician decisions and those outcomes. So one goal of this design is to kind of help ameliorate these issues. So in conclusion, we have implemented a visual clinical decision support system for digital twins in head and neck cancer. And to our knowledge, this is one of the first attempts at a visual interface to explore a digital twin for oncologists in a clinical setting, and one of the few examples of digital twins working with human data. And this work was partially funded by the NIH and the NSF, and we thank our colleagues at the EVL and the MD Anderson Cancer Center.
Okay. Thank you very much. Great talk. Very interesting. I'll start off with one question. We also worked with in a different medical area. We worked with a system that was using similar patients as some support for clinicians, and our observation was the more experienced a medical doctor is, the more he or she would find this helpful. Think about similar patients, and the more junior the doctor was, the more it was on the left side of your slide, the more it was he or she was focused on their training and the knowledge that they gained from earlier training. Did you see the same effect, that the experience was a factor here?
I didn't ask all the individual people their years of experience. We are planning on doing like a more detailed evaluation of the system and adoption, which would include taking in people's actual years of experience. I do know the person that listed the similar patients as their favorite was a full He's been working with us for at least like 6 years.
Mhm.
Most of the people that cared less about like similar patients were people that like didn't work a lot with us, so I wasn't entirely sure about their experience levels.
Okay.
But yeah, that might be an interesting thing to look at. We definitely found that like the people that have been working with us a longer time have liked a lot more information.
Yeah. Oh, interesting. Well, I guess this brings us to the end of our session. It's almost 9 o'clock, and I don't see one pressing question on Slido. Maybe the discussion continues on Discord. I want to thank all the presenters once more, and thank you very much for this interesting session. Thank you for the technical support, and see you soon, hopefully in person. Well, thanks a lot, and goodbye.